This is section 12.1, part 2. So we were working with sigma notation, also called summation notation, by the way. So let's do an example. This time I'm going to use the index k instead of I. So we're going to go from k equals 1 to k equals 6, and our formula is going to be 2 to the k plus 1. Okay. So what that means is we're going to substitute in 1 for k. So it'll be 2 to the first plus 1. Then add to that the substitution of 2 in for k. That'll be 2 squared plus 1. Then add to that the substitution of 3 in for k. We're not skipping any. We're going to use every number from 1 to 6 in order. So the next one we put in would be 4, then 5, and then once we put in 6, the number on top of sigma, that's our last insertion, our last substitution, and we're done. So simplifying, 2 to the first plus 1 is 3, 2 squared plus 1 is 5, 2 cubed plus 1 is 9, 2 to the fourth plus 1 is 17, 2 to the fifth plus 1 is 33, and 2 to the sixth plus 1 is 65. And if you add all those numbers up, you should get 132. Okay. Very good. So, what we're going to do now is we're going to write terms for each series and evaluate the sum if possible. Like on this last one, we were able to evaluate because everything came out to be numbers, and we can add all those numbers up and simplify. So we're going to do that when we can. Some of these we won't be able to simplify. Now, this time I'm going to use the index variable j. And I'm not going to start with 1. I'll start with 3. Our formula this time is a sub j. So this is a generic formula, so there'll be no substitution. There'll be no simplification, excuse me. We will substitute. So the first number we put in is 3. Then the next number we put in is the next bigger number, which would be 4, plus now put in 5, and now finally put in 6, and we're done. That's it. That's all we can do with that one. The thing about starting with 1, and the reason I like it so well, especially since you're just beginning this, it's a little bit hard for you if I don't start with 1. Because when I put in 1, I got the first term. And when I put in 2, I got the second term. And when I put in 3, I got the third term. And 4, I got the fourth term, etc. So all that follows that whatever n is, or in this case k, whatever k is the place it is in the series. It's the fifth term when I put in 5, for example. That's not true here. If I look at the j values that I used here, this is 1. So the first term is a sub 3. The second term is a sub 4. The third term is a, so they don't match. And so that's what makes that a little bit harder, is that the term number and the index number might not agree. And they will agree if your index starts with 1, like the example at the top. This second example here, that's not the case, and so it's a little bit harder to deal with. So if I said, okay, in this, what's the 17th term, a sub what? You're gonna be thinking, oh wow, how do I get that? And what you'll have to do is you'll look for a relationship between j, which is 1, and the subscript 3, 2 to 4, 3 to 5, 4 to 6. Oh, it's 2 more than. So for like the third term, I'd add 2, so that'd be a sub 5. So for the 17th term, it would be a sub, if we went that far. This one stops at 6, but it would be, I say 17, the 17th term would end up being a sub 19, if it's the 17th term. Can't remember what I said now. I think that's what I said. Anyway, so that makes it harder. And so you're going to like starting with 1 a whole lot better. than starting with like 3 or 17 or something. Don't know what the fascination is with the number 17 all of a sudden. Just popped into my head twice in a row. All right, anyway, this one starts at 1, thank goodness, because it is a lot easier. This time, we're going to have a variable expression, x sub I, in our formula. So let's see what we can do with that. So when I put in 1, that's going to be 6x sub 1 minus 2 plus, now I'm going to put in 2, so that'll be 6x sub 2 minus 2. And then I'm going to put in 3 for I, and that'll be 6x sub 3 minus 2. And let's see, if we simplify that, it's 6x sub 1 plus 6x sub 2 plus 6x sub 3 minus 2 minus 2 minus 2 is minus 6. So that's a little bit simpler form for that. And then if someone were to tell us what those stood for, let's let, for example, x sub 1 have a value of 2, and let's let x sub 2 have a value of 4, and x sub 3, let's say that's 6. And so this then in turn would simplify to be 6 times 2 plus 6 times 4 plus 6 times 6 minus 6, which when you do all the arithmetic, you're going to get 66. Right. Okay. And otherwise, if no one had come along and said what you're going to let x sub 1, x sub 2, and x sub 3 equal, you couldn't have finished that any more than what we had right here. That would have been your final answer, the thing I just checked in pink. So you could only go forward if someone told you the values of x sub 1, x sub 2, and x sub 3 for that problem. Okay, so this time we're going to use the index I equals starting with 1, go to 4. Our formula this time is f of x sub I times delta x. Delta is a Greek letter in this form that means change in x, which you may have heard of before. So let's see. And they tell us that f of x is x squared. Okay. And they're going to give us some other things as well, but I don't want to get ahead of ourselves too much. So let's just do the expansion of that first. So we're putting 1 in for each I. That'll be f of x sub 1 delta x plus, now put in 2, that'll be f of x sub 2 delta x. Then put in 3 for I, be f of x sub 3 times delta x plus, now put in 4 for I, that'll be f of x sub 4 times delta x. By the way, this is actually kind of cool. This example's a calculus thing that they're kind of slipping in here on you, which is really kind of cool in my estimation. Anyway, now, since f of x has been said to be x squared, that means that we're going to put x sub 1 into that function and get x sub 1 squared times delta x. Then we're going to put x sub 2 in the squaring function and get x sub 2 squared delta x. And then we're going to put in x sub 3 to the squaring function and get x sub 3 quantity squared times delta x, and x sub 4 squared times delta x. Okay, so that's pretty good. And we're just going to stop with that. That's about as simple as we can get. Now, someone comes along and says, all right, we're going to let x sub 1 equal 0, and we'll let x sub 2 equal 2, and let's let x sub 3 equal 4, and let's let x sub 4 equal 6, and let's let delta x equal 2. Change in x is 2. So this, by substitution, would be 0 squared times 2 plus 2 squared times 2 plus 4 squared times 2 plus 6 squared times 2. And once you perform all of that arithmetic, you should get 112. All right. And I kind of like that they threw that calculus thing in there. You don't know what it means yet, of course, but once you get into calculus, if you looked back at this example, it would make all kinds of sense. You'd be going, oh, that's so cool that we did that early. No, I'm not that big of a nerd, but yes, I am. Yeah, I am. All right, so pi to the 4th over 90 is a way that we can, this series I'm about to write is taking this equation that's where you have pi to the 4th over 90 equal to a series. This series is used to estimate the value of pi. So you'd want to solve this series. That's actually pretty easy to understand what the terms look like. Once you see a few of them, it's like, oh, I get the pattern. So let me write a little bit more of it. Hopefully you have the pattern in your head now. What's going on? Dot, dot, dot. So what would the nth term look like? The one where n is the input. Well, if you said 1 in the numerator, you're right. Divided by n to the 4th plus dot, dot, dot. A lot of times we'll put that plus dot, dot, dot plus our nth term plus dot, dot, dot to show what is the formula that produces each of those terms. So we're supposed to, in part A, use the sum of the first 4 terms of that series to approximate pi. So because we're not doing the whole infinite series, I have to write approximately equal to. So I'm going to do a little bit of simplifying for the first 4 terms. Let's see, 3 to the 4th is 81, and 4 to the 4th is, let's see, 16, 64, 2, 60, no, 256, excuse me, 256. It's 4 to the 4th. Okay, so if we added those 4 numbers together, 1 plus 1/16 plus 1 over 81 plus 1 over 256, and write that answer, it's about, my calculator would not convert it to a fraction, so it must be one of those that the calculator's having trouble with. But I'm not going to type what I'm about to write, I'm going to keep the number in my calculator with all the digits. I'm just writing a few of the digits down sort of as a reminder of what that number was. So what would I do to solve for pi in this equation? Well, hopefully you're thinking, well, first multiply both sides by 90. So that number's still in my calculator. I'm just going to multiply it by 90. It's about 97.0877. Okay, and then to solve for pi, I would take the fourth root to get that principal root of the 4 that exist. Remember that from a previous section. We're wanting the real answer, so and the primary answer, because of course pi is positive, so we wouldn't want to anything that had I in it or a negative answer. So this principal answer is just fine, and so pi is approximately. So I'm going to take this and find the fourth root of it, and that's about 3.13899. I'm going to list a lot of numbers here. 8, I guess that's a good place to stop. Of course, we know that pi is about 3.14159, which this is, kind of close to, but in order to have a lot more accuracy, you'd have to add more terms of that series than just the first 4. So it's close, but it's not very close yet because we haven't added a whole bunch of them. So the next thing asks you to do this the first 50 terms instead of only the first 4. Now that's a lot of typing, and so I don't want you to worry about having to do something of this length. Just kind of realize that someone can type this in and get it to go with relative ease. You just can't on your little scientific calculators do this all that nicely. So plus dot 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 plus 1 over, we said 50, right? 50 to the 4th would be the last one that you typed in. And so if you did all of the calculations on the right side, got an answer, multiplied that answer by 90, took the fourth root of both sides, this is what you'd get. You can imagine how much work that would be if you were typing this in. So anyway, 3.14159. Oh my goodness, this is really close to pi. If you'll type pi into your calculator and hit enter so you can see what it comes up with a value with, it's not the same. Pi in your calculator is 3.141592654. So this part of it back here is not agreeing, but that's agreeing for 1, 2, 3, 4, 5 numbers after the decimal point. That agrees with what your calculator says. So for the first 5 decimal places, that's pretty good. And the more terms you use in this series, the closer you'll get to the exact answer. All right, so some properties of sigma, some summation properties. If we have 2 sequences, a sub 1, a sub 2, a sub 3, dot, 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 a sub n, so that we have the A sequence, if you will, and then another sequence, b sub 1, b sub 2, b sub 3, etc., out to b sub n. We have 2 sequences, and we're going to let C be a constant, any real number for C. It's a constant. And for every positive integer n, which is the domain of all sequences anyway, the following things hold. First, if you have sigma, let's say from I equals 1 to n of a constant that's going to be that number above sigma times c every time. Let's see why that's so. I'm going to give you an example. If I had like from I equals 1 to 4, and I had a constant here like, I don't know, 7. There is no I to put 1 into, so when you put 1 into that formula, you're going to get back a 7. Plus, when you put 2 into that formula, you're going to get back the constant 7. Put 3 into that formula, you're going to get the constant 7. And then put 4 in, the last one, you're going to get 7. And how do we do repeated addition? When there are 4 terms that are each 7? Well, isn't that 4 times 7? N times c. You can see why that works. Of course, we can finish that and say it's 28. But that's how you're going to calculate sigma from I equals 1 to n of a constant. You're going to multiply the number above sigma times that constant and get the value immediately. Okay. Now, some of these I'm going to kind of sort of show you how you can understand why it's true. Others I'll just ask you to accept on faith, because I don't want to spend forever proving these. It's not extremely important that you understand the proof. So if you have a constant multiplied by a formula for a sub I, you can pull that constant out in front of the sigma and multiply the constant times sigma of just a sub I. Let me give you an example of that. Like if I had I equals 1 to 4 of, let's say, 5i squared. So this is 5 times 1 squared plus 5 times 2 squared plus 5 times 3 squared plus 5 times 4 squared, which is 5 as a common factor, times 1 squared plus 2 squared plus 3 squared plus 4 squared, which is 5 times sigma from I equals 1 to 4 of I squared. So that 5 just has come out in front because it's a common factor. That's why that works. Okay. The next two, I'm not going to prove these to you. Just kind of commit them to memory and realize that they are true. So if we go from I equals 1 to n of the sum of two formulas, so a sub I plus b sub I, it turns out that that sigma can kind of be like the multiplication. It's not that, but it's kind of like multiplication of things times something in parentheses, and you can sort of in your mind think that you're distributing that sigma to each of the terms inside. If that helps you remember this formula by saying distribution, that's fine. And by the same token, if you have a sigma formula that involves a difference of two formulas, so like a sub I minus b sub I, that will end up being the sigma of the first one. Messed up. Sigma of the first one minus sigma of the second one. Okay. So those are some properties of sigma that we need to internalize and know those. And then there are some summation formulas that are really nice to know. For example, sigma I, when it's just plain I, from I equals 1 to n. Of course, that means 1 plus 2 plus 3 plus 4, etc., plus dot, dot, dot. until you get to n and you stop, that's always going to be that ending number times that ending number plus 1 divided by 2. Please commit that to memory. Let's do an example of that. Like if I had sigma I from 1 to 4. Of course, what that means is 1 plus 2 plus 3 plus 4. And the reason I picked a small number is to prove to you that it works. And if you add those together, 4, 7, 8, 9, 10 is the answer. Is the formula 4 times 4 plus 1 divided by 2 going to give me that answer? 4 times 5 is 20 divided by 2. Yep, it's 10. That's not a coincidence. That always happens. Okay, so that's a formula for sigma I. Some people call this the sum of the first n positive integers. In fact, on SAT and tests like that, you may have been asked, what's the sum of the positive integers from 1 to 100 or something? And if you'd known this formula, you could have said, well, that's 100 times 101 divided by 2, which is 5,050. And wow, I could have gotten that answer right on the SAT if I'd only known this formula. Yeah. That's why you want to do some of this in high school, so you can learn some of these formulas and get some of those questions on the SAT right without having to mess with them. Okay, this is going to be the sum of the squares of the positive integers, because when I put in 1 and 2 and 3, etc., into that formula, I'm squaring each of those and adding them. And we'll keep doing that until we get to n squared. And the formula that makes this true is n times n plus 1 times 2n plus 1 all over 6. Again, I would like for you to commit that to memory. And then the last one of these that I'd like for you to know about is the sum of the cubes of the positive integers. So this is the sigma I cubed, which will be, of course, when you expand, 1 cubed plus 2 cubed plus 3 cubed, etc., plus n cubed is the last one. And that ends up being n squared times n plus 1 squared over 4. And also make sure that you've committed that one to memory. Okay, so let's see how these are used. We're supposed to use the summation properties and the summation rules to calculate some sigma formulations. So let's say we have sigma from I equals 1 to 40 of 5. And this is where you don't want to write out 5 plus 5 plus 5 plus 5 so that you do that with 40 different 5s added together. You don't want to do that. You want to use this property that since 5 is a constant, this will be the number on top of sigma times that constant. 40 times 5 is 200. And there you go, lickety split. Okay, B. Let's say we had the formula sigma from I equals 1 to 22 of 2i. So that one property says that the constant multiplier times a formula can be brought out in front. So I'm going to bring the 2 out in front so that we have sigma I. And then that's going to be 2 times. And then the formula for sigma I is n, which is 22, the number on top of sigma, times n plus 1. So times 22 plus 1, all over 2. And do that arithmetic, and you should get 506. Okay, C. That's a whole lot faster than adding 22 things together. That's why this is supposed to be good. And that number on top isn't going to necessarily be small like 22 or 40. It could be 643,000, And of course, at that point, you're not going to write down 643,000 things and add them up. So at some point, you have to realize that these formulas are useful. Okay, sigma I equals 1 to 14 of 2i squared minus 3. Okay, so I see a difference of two formulas. So I'm going to write sigma of the first formula minus sigma of the second formula. Okay. Then that 2 is a constant that I can pull out in front of sigma. So let's do that. Leaving I squared inside. Minus, now this one on the right, we're going to be ahead of the one on the left because we're already ready to use the rule for this. So sigma of a constant from I equals 1 to n is the n value, which is 14, times the constant 3. Now, this will be 2 times something. Sigma I squared, if you'll recall, has the formula n, which in this problem is 14. So 14 times 14 plus 1 times 2 times 14 plus 1 all over 6. That's the formula for I squared when n is 14. Minus 42 is what you get when you do 14 times 3. Then when you do all of that arithmetic, this final answer ends up being, let me see, type this into my calculator and see what I get. 1,988. All right. So let's do another one like that. Let's do sigma from I equals 1 to 6 of I squared plus 3i plus 5. So, seeing the additions of various formulas, I'm going to split that into sigma of the first term plus sigma of the second term plus sigma of the third term. Okay. Sigma I squared is going to be n, which is 6, times 6 plus 1 times 2 times 6 plus 1 all over 6. Okay. Yeah, I'm just pausing to think a second, make sure I'm not messing anything up. Okay, plus, now that 3 can come out in front. So this middle part is kind of lagging behind the other parts. That's okay. And then the last thing is sigma of a constant. So that's going to be n times that constant. So in this problem, n is 6, so 6 times 5. So the 6's cancel, that leaves 7 times 13. I'll come back to that later. 3 times sigma I formula is n, which is 6, times n plus 1, 6 plus 1, all over 2, plus, and 6 times 5 is 30. And now if you do all of that arithmetic, you should get 184. Unless I made a mistake. That should be right. Okay, that ends this section. I will see you in class.